All right, so I know I just heard applause in the other room, so I will introduce slowly so people have a chance to come in. Naomi Tack. Naomi is a recent computer science Bachelor of Science, Master of Science graduate from UMBC, so go Retrievers. She focused her thesis on aiding polar scientists in understanding ice sheet data both through computer vision and XR approaches. She interned at APL with QKC last summer and is looking forward to joining full-time in the fall. So please welcome to the stage, Naomi Tack.
Thank you. Hi, everyone. I'm Naomi Tack. I'm here today with my professors and advisor, Dr. Dong Engel and Dr. Rebecca Williams. And I'm going to be going over a bit of my research working with WebXR and polar science. So I got my slides out of order. So here we go. First slide. Overview. So Earth's ice sheets are one of the largest sources of uncertainty with sea level rise. So their melt contributes a lot, not necessarily to sea level rise around Greenland, but other parts of the world where the water flows differently. So we want to know a lot about the topology of the insides of the ice sheet because that informs how ice flows, ice dynamics, that type of thing. We can get information about these internal parts of the ice with ice penetrating radar. So there's a couple ways of collecting that. You can either fly it on a plane over large distances, or you can do like a big truck, which does much more high resolution, but it's a lot slower and you get a lot less area, a lot less data. So we worked primarily with those flight data and using their ice penetrating radar. We visualize these, and I'll show you that in a little bit, what they typically look like in what are called fence diagrams. So when we fly or when we drive the big machine, we go in crisscross patterns or hash marks, whatever you want to think of them like. They're not always nice and perpendicular, though. Often they're like really weird shapes just because of how they fly or how they move. So we visualize these, we call them fence diagrams because they kind of look like fences as they go through, right? But they're often rendered in MATLAB because that's what a lot of polar scientists use. So they're 3D volumes on a 2D surface, so that already you lose a little bit of data, right? So we're like, okay, let's take that, let's put it in XR so you can walk around so you have a better mental model of what the inside of the glacier is like. And because of that, and because of other fields which use this technology, we thought, okay, this will help them better understand, better improve the speed and the quality of their observations, their hypotheses, that sort of thing. So a bit about ice sheets. This is what an ice penetrating radar will pick up and once processed will show you. There's a couple things I want to point out about the image, but you see that dark line up at the top, that is the top of the ice sheet, and above that you see a little bit of white or lighter gray. That's the air in between the plane and the ice, which is a significant distance, but is smushed because of the way the radar is processed. And then at the bottom, you see the bottom dark line, that's the bedrock underneath the ice sheet. And then there's all those little lines, and those are the layers inside of the ice sheet. These layers contain a lot of information, like volcanic eruptions, melt, precipitation. So how much did it snow? How little did it snow? How much it melted at that time period? That kind of thing. And then also volcanic eruptions. You can kind of see some evidence of them down at the bottom. You see these like 3 dark lines going through the ice sheet. Those are called the Three Sisters. They correspond to specific volcanic events a long time ago. They have been able to date those. I don't remember the date off the top of my head, but they date them using ice cores. They drill down into the ice, get a big column, pull it out, date along it. So then they can kind of tag with reference to these radargrams approximately how old the ice is at different places. The data we used comes from CRESIS, which is out of Kansas University. They have a large database full of ice penetrating radar of both Greenland and Antarctica. This slice is taken from Greenland, and it's all freely publicly available over many years, from like 2006 maybe, up to recently. And the reason we can see these layers is, again, because there's different electrical properties inside each layer that can be due to all sorts of different things, including like what's in the air at the time. So here's what the fence diagrams typically look like. This is from the Hercules Dome in Antarctica. So this is south. But this was generated by our coworker and collaborator, Nick Holsch, who's a glaciologist that we've been working with when we developed this. So you can see kind of the crossing patterns. And the reason why we want diagrams like this is because it's really important for polar scientists to be able to trace layers throughout either individual slices and then throughout glaciers as a whole. So diagrams like this will allow you to connect layers in like a horizontal piece with layers all the way down further in the ice sheet. So you can get an idea of what the topography inside of the ice sheet looks like, as opposed to just the surface level. This will help them learn more about how the ice is flowing, how it's moving, that kind of thing. So in order to get these radargrams into a format that we could use, we had to do a lot of spatial positioning, which all of you are familiar with. So I'll probably go pretty quickly over this. Because it's taken from a plane, the elevation varies a lot. So what we had to do was first standardize elevation across all of our radargrams. We took each radargram, converted it into an image, and then used the original radargram to figure out how to make sure all the elevations matched. So our top row of pixels are all the same elevation, but then that elevation is dynamically pulled from the scene itself. So we look at all the images in the scene. What's the minimum highest elevation? And then we pad or crop accordingly. And then we just bound it at the bottom at a set elevation below the bedrock. There's a few rounding errors, so like a pixel might be a few 5 kilometers off, but at such a huge scale, it's not really distinguishable. So we can generally ignore that rounding area. We take the latitude and longitude, we convert it into a flat projection specific to the North Pole, because this is all done in Greenland. And then we have to position it. So we take each radar slice's midpoint and we set it there, do the correct rotation and scaling to get it to be in the lines with the fence diagram. And we did this for 2 locations in Greenland. If you come to the demo, we'll show you one of the locations because it's bigger and a little more interesting. So as you heard earlier, A-frame is really cool. So we used A-frame because of the wide range of community tools. They have spatial navigation, which we needed to tweak a little bit to get it to work with our development, but it was really open source and really accessible. The documentation was significantly better than a lot of the other open source things too, which was a big plus. The other reason we chose WebXR is because of that accessibility. We don't have to have scientists who aren't familiar with VR or computer science at all, nothing to compile, nothing to install. They can just open up their web browser on their headset or computer if it's a tethered one, and go right to the website and pull it up and begin looking at it. It's also independent of that platform. So even if technology changes and as new ones come out, like with the Apple Vision, that should just work as soon as A-frame has the wrappers for the controllers, because that's one of the nice things about A-frame. It wraps the underlying controllers to an interface that you can just use. So some of the controls we developed are scale and rotation. So you can pinch in and out and scale. You can rotate it. You can also just drag yourself through the world or walk around. So think for the handheld controller similar to Google Maps, touchscreen, click and drag and rotate and twist, right? So the reason we did this is because you can use both the hand and the headset control, so you can just walk around, whichever is more convenient for your location. I know when I did development, I couldn't walk too far away from my computer because I had to be connected so I could get all the feedback, so that allowed me to sit still and move around it. But also when I wanted to explore, I could get up and walk around. We have selection of single plane for analysis, so this will be particularly useful when we have annotation implemented because you can just look at one slice and not have all the other slices occluding or increasing the cognitive load on the scientist. We also have opacity similar to how MATLAB has, so you can see through them. That's particularly useful when you're looking at intersections of slices because you want to be able to see, oh, does that layer look like it connects or not? And that's really useful. So here's a little bit about the location. This is a screenshot from the Croesus data site. All the blue lines that you see are flight paths from 2012, I believe. And then that yellow area is blown up, and you can see all the radar slices that I took from the data set. And I also numbered them, and you'll see why in a second. There you go. So that you can connect them to that. The numbering is not there in the XR, but that's just there for your visual reference right now. And we would have something like this if you wanted to actually do some annotation with it. But you can see we have everything lined up in a way that works. And the QR code there is if you want to try it out. You can do it on your mobile phone. It's kind of fun. But we'll also have the demo. But yeah, you can see we have, if you look in 15, you can see how the elevation varies a lot, so it was really important. We had to pad that image up to make sure it aligned with all the rest of them, because in 14, you can't really see it, but the ice does go right up to that top there. And then also with 15, it's right by the coast, so you have some sort of water and that type of stuff, which adds a little bit more fun, right? So we have a couple of ways we recommend evaluating, or we're trying to evaluate this system. One is 3D object recognition. So there's a lot of stuff buried deep within the ice. These things can be things like possibly meteors. It could just be dirt. Even glaciologists don't really know, but they want to identify where they are so they can look at how the ice moves around them, that type of thing. We're also interested in knowing how this visualization would affect collaborative discussions. How does having everyone looking at the same thing help them realize new things, help students learn better? What can we use this for? Is it primarily an educational tool? Is it primarily a glaciologist scientist tool? That type of thing. How does this help their spatial understanding? How does their mental model, looking at the slices on a 2D with a flat MATLAB projection, change or be impacted when they're put in 3D? Is their mental model accurate? That type of thing. And then also layer tracing across disconnected slices. So this is what I was talking about earlier. You have the layers being traced at intersections and going through the volume. So one thing we'd like to do is have that annotation and then be able to hide all the underlying radargrams, so you can just look at your annotation and see, oh, are my lines matching up or not? And have I picked the same layer throughout a large area? So again, some future controls that would be really cool to add. There's a lot you can add to make it a very robust tool. This was initial development and initial prototyping, so it's a little bare bones. But one of the ways we thought about annotating was you could do a simple point and click. There's a lot of paint tools in VR. I tried to get them working. They did not like me, but that's okay. So the simple point and click would be the easiest, but time prevented getting that finished. There's a lot of signal processing algorithms specifically from MATLAB. So we have some that have been converted to Python, which could be run here. But again, ran out of time. And annotation, automatic annotations. This work is part of iHeart. So we have collaborators who are looking at how do we take ML models and annotate radar slices from just a bunch of training data. We have some training data. It's a little sparse, but the models are producing a lot more layers. So once those get up to a higher standard, we can implement them here. And so the talk about implementing AI models, ML models inside XR was really cool. And then also show only annotation. So we only want to be able to see those layers as they're going through the ice, and then we can evaluate those layers. Specifically would be useful for helping evaluate ML models, but we're not there yet. So some future work, it seems promising. Every glaciologist we showed this to was like, oh, this is cool. You should add this, 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 and this, which was great. And I was like, okay, cool. That's a lot of work, and that's hard, but we can do it, yeah. So that was fun. The layer annotations, that way they can show it to students like, oh, this is how you pick a layer, VR. People my age really like, ooh, shiny headset, let's play with it. So I think that's a cool way to engage students. And then just increasing the capabilities of the software as a whole, and then developing like a series of questions, a series of tasks that we can give either to glaciologists or to students to see, okay, how is this actually working? We started the process of that, but whenever you do studies with humans, you have to go through a lot of different IRB approvals, so we didn't get those through in time. But thank you. Feel free to stop by our demo or try it out on your mobile phone. And thanks. That's it.
Yeah, I have a question for you. So you had a small subset. Was there any reason why you didn't use all of your radar data for all of Greenland?
That is a lot of data, and even rendering that seam, A-frame sometimes gets a little bit slow depending on your hardware. With the headsets, it's no problem, but with my laptop, it would slow down significantly. So pulling that amount of data, there's no like workflow pipeline set up, so what I had to do was manually go and find those images and pull them individually. So doing the whole thing is like the end goal, so that you could just select an area and visualize all those slices. But just for the sake of getting something developed and getting something available, we couldn't use that amount of data.
Gotcha. So if you had time, money,
Yeah.
and processing power, you could do it all.
Yeah,
Yeah.
sure, theoretically.
Yeah. And you said those radar images were from 2012. Are there updated images that you could do comparisons against?
Yes, so that's a great question. There are like all the way up into this year. They take like I think it's like a 3-month processing time, and they usually only collect in like 2 months, just because of weather conditions. But the ice moves so slowly that you're not going to see a lot of change, specifically in areas like internal to Greenland. You might see a lot of change in the coast, but that might not be as insightful. So because the ice moves so slowly, that comparison's not going to make too much of a difference. Even in the visualization that I showed you, I think 1 or 2 of the slices were from 2016, but you couldn't even tell the difference in the top layer of them.
Okay, thank you.
Yeah,
Appreciate it. Good work.
So are you tagging the different layers within the icing so you can compare between the different slices? And then, like, were you planning to add something like you could kind of push down through time and have them all cut at the same slice or anything like that? Is that something that glaciologists wanted or whatever?
Like moving like you had with the slicer?
Yeah, but moving down through time, so those like those 3 lines, you could move back to time, see it, and cut out everything above, and kind of going window into time.
That we had not thought of that. That's a really cool idea. I'm not sure if that would be useful or something, but that would be something that we'd want to talk with the glaciologist about and see if that's something that they would be interested in. With the lane tracing, so we have those lines throughout single radar slices, and we're looking at the intersections between them and then other, so we can trace it throughout. We do have some annotated data sets, which we could visualize and throw in, and that's actually how I debugged a lot of this, was we had those annotated ones already, or we could just put a marker at a single elevation and make sure they were aligned. So yeah, that alignment allows for those annotation alignments.
All right, well, if there are no further questions, then please, once again, let's thank Naomi Tack.